Welcome to this lecture series in real analysis. In this lecture, we'll look at particular kind of series, namely positive term series. It's going to be a very simple lecture. So we've learned the root and ratio test, but we won't be needing them. I've just written them here just to recall that. We have learned in the previous two lectures, this is what we learned. Okay. Here are some problems for practice. And now let us get started. So what is a positive term series? A series denoted by this is called a positive term series if each an is non-negative. So already it is a misnomer. We call it a positive term series, but it is actually a non-negative term series. But somehow the phrase non-negative term series is not such a nice sounding phrase, so this has been chosen. Okay. So let's note a very simple but useful or crucial thing, that a positive term series is convergent if and only if the sequence of partial sums is bounded. So why is this? Note that the sequence of partial sums is an increasing sequence or a non-decreasing sequence, right? Because each term is non-negative. So the sequence of partial sums cannot ever take a dip. If the sequence of partial sums was unbounded, then its limit would be infinite. And hence, the sequence of partial sums wouldn't converge because this limit would be infinite. And therefore, the series wouldn't be a convergent series. Right. And similarly, if the series is a convergent series, so we just argued this. If this is convergent, then the sequence of partial sums is bounded. And if the sequence of partial sums is bounded, then the same logic, it is a non-decreasing sequence. The sequence of partial sums is a non-decreasing sequence. If it is bounded, then its limit exists, and that is why this is convergent. So this is a very simple remark. And in the course of arguing this, we have shown that when this happens, meaning when the series is convergent, then the sum of the series is nothing but the supremum of all the partial sums, which is same as the limit of the sequence of partial sums. So we have said all of the things that, it's a very simple thing. I don't want to get into it. You can take this as an exercise if it is not immediately clear. Okay. Also, if we have a positive term series, then we write this to mean that the series is convergent. And we write this to mean that the series is divergent. Right? And in either case, the sum of the series, if it is convergent or not, doesn't matter. What we are going to write down stays true. So this is the nth partial sum as always. This quantity is same as that quantity. If this is a divergent series, then the sum is infinite, if you will, and that is same as this guy. If this is a convergent series, then this is a bounded sequence, and its supremum is same as the sum or the limit of the sequence of partial sums. Anyway, so very simple. All of these things are very, very easy. If your basics are right, if you studied sequences well, all of this should be obvious. Okay. And yeah, one thing I wanted to say is that this note is not valid if we did not have the assumption that our series is a positive term series. For an arbitrary series, it may very well happen that the sequence of partial sums is bounded, but the series is not convergent. For example, you can take this series. The sequence of partial sums is bounded. It never goes above 1 and never comes below 0. But still, this is not a convergent series. The sequence of partial sums does not converge. Anyway, alright, so more notation. Suppose we have any series, then for each finite subset f of the naturals, we write S sub f to mean the sum of all the ANs where n is coming from f. The sum along f, if you will. Right? So our usual, what was our usual thing? Our usual thing was Sn, right? This is the sum of the first n things. So Sn in this notation is nothing but S sub this particular finite set. This looks ugly, this looks neat. Okay. So again, this time we have some positive term series. Then this supremum, which is same as, well, if this is convergent, then this supremum is same as the sum or the limit of the sequence of partial sums. If it is divergent, even then, this supremum is infinite and same as, it makes sense to say that this is also infinite. So this supremum is same as this supremum where f is a finite set. Right, so this is again a very simple thing. Why is this true? Well, note that this is dominated by that. That's very clear because all the Sns are already appearing in this set. So if you take the supremum, of course this will dominate the left side. We need to show the other direction, but that's also very easy because if you pick any finite set f, you consider S of f, you can find some natural number such that f is contained in this much. Clearly, in fact, you can take little n as the maximum of all the things in capital F. Right? So, this is of course dominated by S sub n, and this is, we use the hypothesis that it is a positive term series, otherwise we can't say this. So we have that. So anything in this set is dominated by something of this sort, and hence if you take the supremum on both sides, the left side will dominate the right side. So we have both inequalities and hence these two things are equal. It's a trivial statement, but it is still good to record it. Okay. So let's proceed. Now for something interesting. Perhaps this is the only interesting thing in this lecture. So first we define what is a permutation of naturals. A permutation of the natural numbers is any bijection of the naturals with themselves. So what is the idea? All you're saying is that you're relabeling or rearranging the positions of the things in the set of natural numbers. Right? It's a bijection, so you are saying that, well, 1 goes to some place, 2 goes to some place, 3 goes to some place. Possibly their places have changed. Originally 1 came the first, 2 came the second, 3 came the third. But after you apply this bijection, the positions may have shuffled. But there is no collision. It's a bijection after all. So all that's happening is that every natural number has occupied a new position in this ordering. So you're permuting the elements of the natural numbers. That's why it's called a permutation, even though we could have just called it a bijection from n to n or whatever. But this terminology is also used in group theory. You can have any set here, a permutation of x is just a bijection of x with itself. That's the definition, but here we only will be talking about natural numbers. Okay, so now suppose we have a series. Then another series is called a rearrangement of the original if there is a permutation sigma such that Bn is a sigma n. So you have rearranged the terms of the series via the permutation sigma, and that forms a new series. Right? So here we are not saying we are dealing with positive term series or anything. These definitions are general. Right? And a very important note, and this is the most interesting thing in this lecture, is that a series may be convergent, but its rearrangement may not be convergent. So what I'm saying is that you can have a series which is convergent, but it is possible that it admits a rearrangement which is not convergent, and let me explain that via an example, even though I'll not be very, very formal. So consider this series. So A1 is this, A2 is that, A3 is this, A4 is that, and so on. Clearly, this is a convergent series because you take any partial sum. The first partial sum is half, the second is 0, then 1/3, then 0, then 1/4, then 0. Clearly, that is a convergent sequence. So the sequence of partial sums is convergent, and hence, this is a convergent series. I want to argue that it admits a rearrangement which is not convergent. So for that, recall that this series is divergent, and it is a positive term series, so I might just write this is equal to infinity. It just means that the sequence of partial sums is unbounded. Okay, so using this fact, I want to argue that this particular series admits a rearrangement which is not convergent. So the point is, I'll pick the positive terms that appear here and start writing them down. Maybe I'll use a different color. And I'll go up to the point when I cross 1, when this thing crosses 1, and it has to because of this fact, at some point I will have crossed 1. So let's say I have crossed 1 at some natural number n1. Maybe I'll use capital N1. Now I start writing negative terms. And I will keep writing them up until I reach n1. Right? So this I placed here, this I placed here, this I placed there, and this I placed there, then there, and so on. So I have so far rearranged some finite chunk. This crossed 1, but I have pulled it back down to 0. Now again, I'll continue my journey from this point. So I will write, maybe I'll put all of this in a bracket. I hope this doesn't confuse anyone. And then I'll start writing these things. And up till what point? Up till where this whole thing exceeds 1. Why should such an n2 exist? Well, again, this is some finite number after all. And since this is infinite, there has to be some n2 such that this whole thing is bigger than 1 plus this thing. This is some finite number. This is something that I have in my hand. So there has to be some capital N2 such that this whole thing is bigger than 1 plus this guy, and hence this whole thing will be at least 1. And again, I'll bring it back down to 0 by using the negatives of them. So this series that I'm writing should be evidently a rearrangement of the upper one, right? I've just kind of pulled things and literally rearranged them by hand. Right? So a series may converge, but its rearrangement may not converge. However, in case of a positive term series, this pathology doesn't arise. If you have a positive term series and you rearrange via any bijection, then the convergence of the original is equivalent to the convergence of the rearranged. In fact, they have the same sum. So you should take this as an exercise and not worry about what I'm going to write down. But if you're feeling particularly lazy, let me give you an argument. So here is the proof. So recall, we have this notation, SF denotes this, and define TF as, so let me call it Bn. This thing I'll call as Bn. So TF is defined as sum of Bn's along F, right? But again, by definition of Bn, this is nothing but that, but note this is equal to this thing. Now what happened? What is this? This is the image of F under sigma. Sigma is a function from naturals to naturals. So every subset of naturals becomes a subset of naturals under sigma. The image of F is sigma F, just a usual set theoretic notation. So clearly this is equal to that, and therefore this is equal to S sigma F, right? So finally, as we have noticed before, that this sum, since it is a positive term series, this is equal to the supremum of SF. F is a finite subset of natural, so everywhere F was finite. So this we had observed earlier. This I want to say is equal to, so this is something to note, this is equal to supremum S sigma F. F is a finite subset. So why are these two supremums same? Well, these two sets are same, right? Every possible finite subset of naturals is the image of a certain finite subset of naturals. Every finite subset of naturals is obtained as the image of some other finite subset of naturals, because all you do is you pull it back via sigma and that's it. That is the finite set whose image is the one that you wanted. So these two sets are same. A trivial remark, but may be confusing. All right. So this is equal to supremum TF by definition of TF. But this is equal to the summation or the sum of the rearranged series, right? TF was this, and we have already noticed that if you take the supremum of, partial sums along finite subsets, you get the sum of the positive term series. So this whole thing argues these two things simultaneously, and I will leave it at that. So with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.